So I'm Isabel Bertia. I'm here to introduce you to Chapter 6, which is the concurrent process. So, what is the parallel processing? Parallel processing is a situation in which two or more processors operate in one system at the same time and may or may not work on related activities. In other words, the CPU executes instructions simultaneously, and the processor manager has to coordinate activities of each processor while synchronizing cooperative interactions among all of them. The two primary benefits of the parallel processing system are increasing reliability and faster processing. So, the increase in process speeding can be achieved when instructions or data manipulation can be processed in parallel, two or more at a time. Some systems allocate a CPU to each program or job. Others allocate CPU to each working sets or parts of it. Still, subdivide the individual's instruction so that each subdivision can be processed simultaneously, which is called concurrent programming. Then the increase of flexibility brings increase also in complexity. However, and the two major challenges remain, like how to connect the processors into a workable configuration and how to orchestrate their interactions to increase the overall system efficiency. So there are also levels of multiprocessing. But first, what is multiprocessing? Multiprocessing can take place at several different levels, each of which tend to require different frequency of synchronization. At job level, which is this one, processing multiprocessing is fairly benign. It's as if its job is running down on its own workstation, which shares systems resources. On the other hand, when multiprocessing takes place at the thread level, a high degree of synchronization is required to disassemble process to perform the thread's instruction and correctly reassemble the process. So there are three columns, and each column is a para, parallelism level, process assignments, and synchronization required. These are the typical levels of parallelism, and they require synchronization among the processes. At job level, the process assignment is each job has its own processor, and all the processes and threads are run by the same processor. So in the synchronization required, no explicit synchronization is required after jobs are assigned to a processor. Next, in the process level, the process assignment is unrelated processes, regardless of job, can be assigned to available processors. So it can be two or more processes or one, as long as it's available processor. So in the synchronization required, a moderate amount of synchronization is required. Next is the thread level. Threads, regardless of job and process, can be assigned to available processors. So its synchronization required is a high degree of synchronization and is required to track each process of each thread.
For this part, I'm Din Archie Pimalyari, and for this part, I'm going to talk about multi-core processors. So this part will introduce to you uh, three three types of processors. They're multi-core processors, and and I will show you why the designs have benefits and have disadvantages. So this is the master-slave configuration where there's an asymmetric multiprocessing system. As you can see here, there are arrows, and it shows that some parts have two-way communication and some parts have only one-way communication. This is a typical uh, typical configuration of design of the next processors and this processor. As you can see here, uh, the processor is dependent on the main memory, and because of this, it takes a pretty long time before it it's a disadvantage because when the main memory, the reliability is no higher than it is for a single processor system, because yun nga, pagkabag yung master processor nag-fail siya, masisira yung buong process. Tapos ayun, poor use of resources kasi kapag free yung slave processor, ah, yung master processor dapat busy rin. So ayun, yung number 3, sinasabi, it increases the number of interrupts because all slave processors must interrupt the master processor every time they need operating system intervention. So yun nga, it's too dependent on the too dependent. So susunod naman is yung loosely coupled configuration. Makikita mo dito merong yung tatlong processors, tapos tatlong input output, tsaka tatlong main memory. Ito yung parang uh, nawawala yung dependency niya. Tapos ayun, when the job arrives for the first time, it is assigned to one processor to keep the system well balanced and to ensure the best use of resources. Job scheduling is based on several requirements and policies. Tapos yung then this isn't prone to catastrophic system failures because yun nga, tatlo yung processors, hindi katulad nung kanina, isa lang yung parang nakadepend dun yung buong whole processing na process. Ito naman yung symmetric configuration, makikita nyo dito, tatlo naman yung processors, tapos isa lang yung input-output device. Tapos ito yung mga advantages niya. It's more reliable, it uses resources effectively, it can balance loads well, and it can decrease gracefully in the event of failure. Pero yun nga, ito yung pinakamahirap daw na configuration to implement kasi kailangan natin ng pagiging synchronized para ma-avoid yung graces and deadlocks, which will be discussed by the next chapter. So yun nga, whenever a process is interrupted, whether because of an input-output request or another type of interrupt, its processor updates the corresponding entry in the process list. Kasi nga, para ayun, ito yung pinaka-advantages nga, pero ito yung pinaka-complicated na processing uh, processing na way. So thank you for listening.
Hello and welcome everyone. My name is Jana Raydon and I'm here to present about process synchronization software. So why use process synchronization software? As stated from the previous topics, we can deal with multiple processors, and if we do that, it means that there'll be multiple jobs and multiple processes that needs to be processed. So it invites chaos into the system by creating mistakes that lead to leaving a job to wait indefinitely, causing starvation, or if it's a key resource, cause deadlock. For example, you have restrooms, and then you need to use the restroom, but there's no indication if it's being used. So you just open up the door, then you're shocked that someone was there. Then that's a good example of a bad synchronization, which clearly means that he didn't know that there was someone using it, so he just went on and opened the door. So that's a bad synchronization. So yeah, chaos is no synchronization. If anyone gets a reference. What are the basics of process synchronization? Well, the success of process synchronization hinges on the capability of the operating system to make a resource unavailable to other processes while it is being used by one of them. These resources could be input-output devices like your mouse, your monitor, keyboard, scanners, a location in storage, a data file, etc. the basics of process, if a resource is being used, it is locked away from other processes, and then only released when it is over to be used by other processes. Which means, for example, like in here, you have processor 1 and processor 2. Both of them are presented job 74. And the next job will increment to plus 2, because both of them got presented with 76. So what happens to 75? Well, it won't be used, because this is what happened. So in this case, instead of every job getting processed, one got ignored because two processors ignored job 75 because both of them was given job 74. So this is one of the reasons why process synchronization softwares are used. And how does process synchronization software works? They have a critical region. This is where the synchronization comes in. The common element in every synchronization schemes is to allow a process to finish work on a critical part of the program before other processes have access to it. This is called critical region because the execution must be handled as a unit. Synchronization as lock and key arrangement. This means that if in most of the process synchronization softwares, if you have a job, this is presented to a processor, then that processor will be locked because it has a job already. Then it will execute the job that it is assigned on. Then it will unlock once it's over. Then rinse and repeat, just like that. There are a couple of locking mechanisms developed. We have test and set, wait and signal, and the semaphores. So basically, the test and set is a single, indivisible machine instruction that was introduced by IBM for its early multiprocessing computers in a single machine cycle. It tests to see if the key is available, and if it is, sets it to unavailable. What this means is, just like what I said earlier, if there's a processor that is being used, a resource that is being used, then it will be put in a busy mode, which means that it will generate a key, then it will be set to 1, which means it's busy, so it won't be able to be used by other jobs. As seen in this pseudocode, if key is equal to 1, you test and set, because it will test if, again, if this resource is busy or available. It keeps on repeating that until it becomes 0, which is available. Then if it's 0, then they set the key to 1, so it will notify the system that it is busy, then it will proceed to executing the job. So what's the catch if it's so simple? First, when many processors are waiting to enter a critical region, starvation can occur because the processes gain access in an arbitrary fashion. Unless a first-come, first-served policy is set up, some processes could be favored over others. And secondly, the waiting processes remain in unproductive, resource-consuming wait loops requiring context switching. This is because the processes repeatedly check for the key. This is known as busy waiting, which not only consumes valuable processor time, but also relies on competing processes to test the key. Sometimes that is best handled by the operating system or the hardware. The first problem that we encounter using test and set means that sometimes two jobs could come into the resource, which should cause a confusion. So the resource wouldn't know who came first, so it will increment just like the problem before, it incremented 2 times, so it skipped a job. So there's a problem for the first problem. And secondly, since there's a lot of context switching and consuming wait loops, it uses a lot of resources. So it repeatedly checks for the key, as shown in in this pseudocode. It repeatedly checks if the key is busy or available. So it's in an unending loop. So it consumes a lot of resources. And then we have the wait and signal. Wait and signal is a modification of test and set that's designed to remove busy waiting. Two new operations, wait and signal, are mutually exclusive and become part of the process scheduler's set of operations. So basically, wait and signal is just like a queue, if you're familiar with queues. So every job is lined up, then each one of them is attended one at a time. Then it's basically first come, first serve. What are the step-by-step of the wait and signal? Firstly, wait is activated when the process encounters a basic condition code. Wait sets the process control block, or the PCB, to the blocked state and links it to the queue of processes waiting to enter a particular critical region. Second step is the process scheduler then selects another process for execution. And then signal is activated when a process exits the critical region and condition code is set to free. That's when the job is finished, so it's set to free. Then it checks the queue of processes waiting to enter the critical region and selects one, setting it to the ready state, which means it will be ready for another job to receive, and it will repeat again. And the third one is the semaphore. A semaphore is a non-negative integer variable that can be used as a binary signal or a flag. By definition, it can have exactly 2 positions, no more nor less. One good example of a semaphore is a signaling device that is used for railroads to indicate whether a section of track is clear or not. This can be seen in your railway stations, like the PNR, the España station, every train. Basically, only España station. Only PNR has this, I think. Then, if the hand is raised, it means that the track is clear, and if the hand is down, then it indicates that it should stop. People should stop. Semaphore. Oops. So semaphores in operating systems. In an operating system, a semaphore is either a 0 off or 1 on to perform a similar function. It signals if and when a resource is free to be used by a process. It was first introduced by Edster Dijkstra at 1965. He introduced 2 operations to overcome the process synchronization problem. So what are these operations? Basically P, which stands for the Dutch word to test, and V, which stands for verhogen, to increment. The P and V operations do just that. They test a condition, then they increment it. So how does Semaphores work for process synchronization software, you might ask? Well, if you let S be a semaphore variable, then the V operation on S is simply to increment S by 1. The action can be stated as this in turn necessitates in a fetch. Oh shit. So how does Semaphores work as process synchronization software, you might ask? Well, if we let S be a semaphore variable, then the V operation on S is simply to increment S by 1. the action can be stated as V's of S. S is equals to S plus 1. This in turn necessitates a fetch to get the current value of S, increment to add 1 to S, and store sequence performed as a single indivisible action. This means the meaning of performing single indivisible action is to make everything go at once, so there won't be any confusion on who went first from the problems stated as before, like the first come first serve. The operation P on S is to test the value of S, and if it's not zero, to decrement it by 1. The action can be stated as P's of S. If S is greater than 0, then S is equals to S minus 1. This involves a test, fetch, decrement, and store sequence, also performed as a single indivisible action. Here is an example of a Semaphore. Just like in the test and set scheme, this time, if S is equals to 0, the critical region is busy, hence the process calling for the operation must wait until the operation can be executed, and that only what happens when S is greater than 0. At this example, at state 0, we can see that there is no calling process, no operation, so the value is 1. Nothing's happening yet. And then at state number 2, we have a calling process, which is P1. Then it gets tested. So it's already running in critical region. So we decrement the value of S by 1, so it becomes 0 again. Then we have a state number 2. Then we have we still have the process P1 still in there, so we increment by 1. But process P1 is already over at that point, so they decrement it by 1. I mean, they increment it again, so it states that it's free again. Then we have a state number 3, where we have a calling process P2. So we test it, and then we all know that it's in critical region again. So we decrement the value of S by 1 again. So we have 0. And then at state 4, we called for P3, and we can see here that P2 is still running in critical region, which means the S will be still be 0, which means P3 will be blocked due to S being still 0. Then we have state 5. At state 5, we have another process being called upon, and it's P4, and we can see that P2 is still in critical region, which means S is equal to 0. Then, in turn, we will have two processes that will be blocked, P3 and P4. Then, at state 6, there's a calling process for P2, which increments the S, which means P2 is over, and now another process can be called. And then we can see here P3 is in critical region now, and only P4 is being blocked at this moment, which means S is equal to 0 again. Then we have state 7, doesn't call any processes, so operation is nothing, but it's still running in critical region for P3, and P4 is still blocked by S because it's 0. Then we have at state 8, incrementing S, in turn stating that P3 is already done. Then, which means P4 can run in critical region now. So we can see here nothing is getting blocked by S anymore, since the last calling process was P3, which was to end it. And then S is still 0 because P4 is in critical region. And then we have state 9, which calls the process P4, which then increments it, with meaning the process just ended. And nothing else is in critical region, which means the value of Fs is 1. So what is this type of semaphore called? This type of semaphore is called a mutex, short for muted, for mutual exclusion. Since the processes are getting mutually excluded from from the use of the operation, therefore the operations become test of mutex. If mutex is greater than 0, then mutex is equal to mutex minus 1. That's the S that is stated earlier in the example. And then we have increment mutex, which states that mutex is equals to mutex plus 1. That is all. Thank you.
Good day, I'm Justin R. Parubrup and I will discuss about process cooperation. Process cooperation are those that can affect or are affected by other processes running on the system. Process cooperation will share data with each other. There are occasions when several processes work directly together, cooperatively, to complete a common task. Two famous examples are the problems of producers and consumers and of readers and writers. Each case requires both mutual exclusion and synchronization, and each is implemented by using semaphores. The reasons for needing process cooperation. There may be many reasons for the requirement of cooperating process. Some of these are given as follows. First, modularity. Modularity involves dividing complicated tasks into smaller subtasks. These subtasks can be completed by different cooperating processes. This leads to faster and more efficient completion of the required task. Second is information sharing. Sharing of information between multiple processes can be accomplished using cooperating process. This may include access to the same files. A mechanism is required so that the processes can access the files in parallel to each other. Third is convenience. There are many tasks that a user needs to do, such as compiling, printing, editing, and etc. It is convenient if these tasks can be managed by cooperating processes. 4. Computation speed up. Subtasks of a single task can be performed parallelly using cooperating process. This increases the computation speed up as the task can be executed faster. However, this is only possible if the system has multiple processing elements. Methods of cooperation. Cooperating processes can coordinate each other using shared data or messages. Details about these are given as follows. First, cooperation by sharing. The cooperation process can cooperate with each other using shared data such as memory, variables, files, databases, etc. Critical session is used to provide data integrity and writing is mutually exclusive to prevent inconsistent data. The cooperation by sharing, it gives maximum speed and convenience and it is more faster than cooperation by communication. As you can see in the above diagram, process P1 and P2 can cooperate with each other using shared data, such as memory, variables, files, databases, etc. Second is cooperation by communication. The cooperating process can cooperate with each other using messages. This may lead to deadlock if each process is waiting for a message from the other to perform a operation. Starvation is also possible if a process never receives a message. So, the operation by communication is useful for exchanging small amount of data. In the map diagram, process P1 and P2 can cooperate with each other using messages to communicate. So, the producers and consumers. The classic problem of producers and consumers concerns one or more processes that produce data that one or more process consumes later. Let's look at how they can do so by using a single buffer, beginning with the case of one producer and one consumer. Although current versions would almost certainly apply to systems with multiple producers and consumers. Returning for a moment to the password framework introduced at the beginning of this chapter. The synchronization between one producer's process and one consumer's process, the cook and the bagger, represents a significant issue when it's applied to operating systems. The cook produces hamburgers that are sent to the bagger, who consumes them. Both processors have access to one common area, the hamburger bin, which can hold only a finite number of hamburgers. The bin is essentially a buffer. The bin is a necessary storage area because the speed at which hamburgers are produced is rarely the exact same speed at which they are consumed. So, sa figure sa may gilid, producer is the cook and consumer is the bagger. So, itong buffer flow, para ito yung tinatawag na hamburger bin. Sa mga fast food, di ba nakikita nyo yung pag bumibili kayo, di ba? Yung si consumer, yung kinukuha nyo yung mga burger, ayun yung hamburger bin. Kumbaga, kung ano yung gagawin ni producer, ayun yung kukunin ni bagger. So, pag walang ginawa si producer, walang makukuha si bagger. So, isa siyang problem. And, pag hindi naman kumuha si consumer, tas produce lang na produce si producer, isa pang problem yun kasi mapupuno yung buffer flow. So, yeah, next. Problems arise at two extremes. When the producer attempts to add to a bin that's already full, which happens when the consumer stops or withdraws from the bin, and when the consumer attempts to make withdrawal from a bin that is empty, such as when the bagger tries to take a hamburger that hasn't been deposited in the bin yet. In real life, the people watch the bin. If it is empty or too full, they quickly recognize and resolve the problem. However, in a computer system, such a solution is not so easy. Consider the case of the prolific CPU that can generate output data much faster than a printer can print it. Therefore, to accommodate the two different speeds, we need a buffer where the producer can temporarily store the data so that it can be retrieved by the consumer at a slower speed, thereby freeing the CPU from having to wait unnecessarily. This buffer can be in many states from empty to full. The essence of the problem is that the system must make sure that the producer won't try to add data to a full buffer, and that the consumer won't try to make withdrawals from an empty buffer, because the buffer can hold only a finite amount of data. The synchronization process must delay the producer from generating more data when the buffer is full. It must also be prepared to delay the consumer from retrieving data when the buffer is empty. Notice that when there is only one producer and one consumer, this classic problem becomes a simple case of first in, first out. However, when there are several producers, consumers, a deadline occurs, they are all paused as they wait to be notified that they can resume their respective deposits and withdrawals. That's all. Thank you.
Good day. So I'm going to introduce about the concurrent programming. So until now we have looked at multiprocessing of several jobs executing at the same time on a single processor or on multiprocessors. This concept is not new, but it requires a programming language and a computer system that can support this type of concept. So this type of system is referred to as a concurrent processing system, and it can generally perform data level parallelism, instruction level parallelism. So when it comes to concurrent programming, we have to understand types of parallelism. There are generally two: data level parallelism and instruction level parallelism. Let me explain the instruction level parallelism first. So it refers to systems that can perform multiple instructions in parallel. According to Wikipedia, it is a measure of how many of the instructions in a computer program can be executed simultaneously. So for example, we have three individual instructions: is set to A plus B, F is C plus D, and M is set to E times F. So as we can see, instruction 3 only can be calculated after E and F are set from instructions 1 and 2, while instruction 1 and 2 are independent, which means there is no problem to be solved at the same time beforehand. So therefore, we can build a program doing the instruction 1 and 2 at the same time, and followed by instruction 3. And next, data level parallelism. It is a system that can perform on one or more streams or elements of data. For example, there is an instruction that tells to get the sum of elements in an array that contains number 1 to 10. Instead of adding 1 by 1 from 1 to 10, applying data level parallelism here, dividing the data sets and getting sum of its divided data simultaneously and getting the total sum of them is possible. And next, Flynn's taxonomy. It describes machine structures that fall into four main classifications of parallel construction with combination of single and multiple instruction and single multiple data. Each category presents different opportunities for parallelism. So we have four categories, and each category presents different opportunities for parallelism. So we have the single instruction single data, or SISD, and multiple instruction single data, MISD, the single instruction multiple data classification, which is SIMD, and multiple instructions multiple data, MIMD. So there's just combination of parallelism. We just have to understand what types of data and instructions were used. And now we might come to think and expect that as we have more processors, it is faster to finish your job, but it is not always true. So regardless of a system's physical configuration, the result of parallelism is more complex than initially thought. Jean Amdahl proposed in 1967 that the limits of parallelism processors could be calculated. We can just refer to this formula and the graph. So in its simplest form, Amdahl's law maintains that if a given program would take 1 hour to run a completion with one processor, but 80% of the program had to run sequentially, and therefore could not be sped up by applying additional processors to it, then the resulting program could only run a maximum of 20% faster. Interestingly, Amdahl used his work to promote the use of single processor systems even as parallel processors were becoming available. And next, order of operations. So there are steps to solve the equation. So first, calculation in parentheses, and next, exponents, and third, multiplications and divisions. And fourth, we do addition and subtractions. So we solve equations by these steps. So can we evaluate an equation faster if we use multiple processors using parallelism? So we'll be using two terms that are co-begin and co-end. They identify the instructions that can be processed concurrently. For this equation, let's assume that a sufficient number of CPUs are available. So when you see the given equation, we have 7 steps, total of 7 steps. So when we rewrite our expression to place the result in 3 temporary storage locations, T1, T2, T3, and so on and so forth, with co-begin and co-end, it may look like this. So there are 3 instructions that start at the same time and stored in temporal 1, 2, and 3. And next, temporal 4 and temporal 5. And we have last instruction for the result. So it may look like this graphically. 3 is the sufficient number of CPUs for this problem, so we could shorten the 7 steps process into 3 steps. So with this system we have increased the computation speed, but we have also increased the complexity of the programming language and the hardware. In fact, we have also placed a large burden on the programmer to explicitly state which instructions can be executed in parallel. This is called explicit parallelism. So our original equation does not need to be rearranged. When the compiler automatically detects the instructions that can be performed in parallel, this is called implicit parallelism. And when the compiler automatically detects the instructions that can be performed in parallel, it is called implicit parallelism. So we rearrange the equation for better parallelism rules. So we can conclude that the advantage of explicit parallelism programming is the absolute programmer control over the parallel execution, while implicit parallel programming has an advantage for a programmer, that there is no need to worry about task division or process communication, etc. So we actually can focus on the program. So there are applications. Of concurrent processing. So you can also dramatically reduce the complexity of work with array operations within loops, or performing matrix multiplication and conducting parallel searches in databases, or data mining, and of sorting or merging files. Some of these systems use parallel processors that execute at the same time of tasks. Thank you.
Hello, good day. I am Jonathan Begisi, and today we will be talking about threads and concurrent programming, as well as the two languages involved in concurrent programming. So, from the previous chapters, we learned that traditional or heavyweight processors are frequently swapped between the main memory and the secondary storage during execution. And what it does is to accommodate multiprogramming at the same time take advantage of its existing virtual memory. So this results to overhead time, in which somewhat occurs when an information needed to be saved. It's like a lag, it's like a delay. So the solution for this overhead time is the implementation of threads or lightweight processes within the operating system. So what are threads? So threads are basically passive small units containing processes which can be scheduled or executed. They can communicate easily because they share the same resources as the process that created them. So these threads are also supported at kernel and user level, which means it can be managed by operating systems or its own software. So next, the processes use several active threads for efficiency since needed information amount is being reduced. It switches a thread to another very quickly, in which the CPUs create multiple threads that are executed in parallel or executed at the same time. So taking a small active thread, a single thread, it has its own registers, counters, stats, and status in which these resources can be shared to within the data area and resources allocated to its process. So going to the counters, they are basically variable storage dynamically created by the process. So multiple threads can communicate more efficiently since they share the same resources and space, promoting processes capabilities. In other words, a thread can have specific tasks from one another, each responsible for certain tasks a processing is undergoing. So next. So going to the two concurrent programming languages. First, we will go for ADA. So the early programming language didn't support threads, creation, or concurrent processes, but rather done in a serial manner or step by step, giving the user the option to create a single process or a thread of control. So the following will be one of the early concurrent programming languages in the late 1970s, one of which is ADA language and the other is Java. So focusing on Ada language first, it is named after Augusta Ada Byron, one of the allegedly, I don't know, allegedly one of the considered as first programmers in the world, in which the language was made open for the public in 1980s, which was commissioned by the US DoD or Department of Defense, supporting concurrent processes and embedded computer systems found in military arsenals. Military arsenals such as guided missiles, jets, ships, navigation systems, and that sort of things. So the language was used to be modular in order for programmers could work by sections, which scalability comes into play, of a large project uniquely from others, allowing contracting organizations to compile theirs separately and have a finished product assembled once its components were done. So the Department of Defense or DoD implemented a global authority for this to prevent adaptations of the language into mutually incompatible subsets or supersets. So they've done this for standard purposes. So next. The DoD's course of action was to make the name ADA a trademark, making the language into an ISO, one of the standards, existing standards here. With the aid of IEC committee consisted of several countries. Countries such as Japan, America. So International Standard Organization or ISO standard was later updated from ADA 2005 to ADA 2012, revising some of its objectives regarding object-oriented programming as well as real-time and high-integrity features. It was also guided by ADA reporter group, who were a committee in charge with drafting and revised standards. So next, the other early programming concurrent programming language is Java. So Java was introduced in 1995 as a universal software platform for internet applications. The language allowed programmers to code applications with capabilities to run on any computer. So Java was created so that there will be a common ground for each of the computers, each of the existing computers. So the language was an attempt to solve several issues, which are the following. First is the costly developing software applications for each of many incompatible computer architectures available. Next is to meet the needs of distributed client-server environments. And lastly, the implementation of growth of the internet and the web. So it is to accommodate, basically. It has the feature of both compiler and interpreter. It's first of its kind, in which its source code was first compiled into an intermediate language called Java bytecodes, in which it was a platform independent, making it run on any computer that has a Java interpreter. These features gave way for it to fit into a hardware and operating systems specifications that will run its language. So with the Java, there are three segments that makes up the Java programming language. So the first one is the Java platform. So it is a software-only platform that runs on top hardware-based platforms. It is comprised of two components. So one of its components are Java VM or virtual machine. The other one is Java API, which is the application programming interface. Excuse me. So Java VM virtual machine is the foundation of the Java platform, in which it contains a Java interpreter. So it runs on bytecodes provided by the compiler. It is on top of many different hardware-based platforms. and a process is used to shield its program from computer hardware. So next one is the Java API, or the Application Programming Interface. So it is a collection of software modules that programmers use in their applications, in which it is grouped into libraries or packages of related classes and interface. It's like it's like one of the classes, or one of the libraries that we can use in C++, C#. It provides basic data types to input-output functions, from network interface to GUI kits. So lastly, a Java language environment. So it is an object-oriented programming created for the purpose of accommodating different platforms without requiring adjustments for each platform. Its syntax was based on C++ programming, in which they've done it so that programmers can easily learn it. It has unique features such as memory allocations, compilation time, and its memory allocation and referencing models being not visible to programmers but are controlled by underlying runtime platforms. It has a secure feature and runtime system, as well as compile time and runtime checking for creating reliable software, as well as method synchronization. So let's say executing its program can request particular classes to be loaded from the network. In firstly check by a verifier to ensure code correction, and next is safety to run without risk. It also supports multi-threading, which we talked about earlier, at language level in the form of threads class, in which it is a collection of methods used for run, start, stop, and check the thread status. So Java threads are preemptive and time sliced depending on the Java interpreter's platform. So that's it. That's the end of our discussion. Have a good day.